collisions involving conservation of momentum, specifically elastic versus inelastic collisions, the topic of 4.3. So elastic collisions. An elastic collision is defined as a collision where kinetic energy is conserved. Example, if we look at billiard balls as they rebound off each other, billiard balls will tend to have the same speed before collision as they do afterwards, hence indicating to us that they have that the billiard ball collision is elastic. Oh, give you a second there to write that down. We don't have too much to cover here. So now we move on to inelastic collisions. So if elastic collisions are where kinetic energy is conserved, inelastic collisions is a collision where kinetic energy is not conserved. So an example would be a car crash. When car crashes happen and they rebound off each other, cars move significantly slower than they do prior to the crash, indicating to us that the kinetic energy they had before the collision is greater than the kinetic energy they had after the collision. In these cases right here, what tends to happen is that the kinetic energy is not destroyed, but it's converted into thermal energy, aka heat. So when a collision occurs that's inelastic, the kinetic energy is converted to heat. If the two objects interlock, what we say stick together, after the collision is a perfectly inelastic collision. So example, car crashes where cars interlock or stick together are representative of perfectly inelastic collisions. So summarizing conditions for collisions. One important thing to note that's a big misconception is people tend to think that momentum is not conserved in an inelastic collision. Momentum is conserved in all collisions where we do not have friction from the ground acting. And again, in most cases we talked about, unless it states friction in the problem, we are assuming no friction acting. So whenever you have a collision, regardless of being elastic, inelastic, or perfectly inelastic, momentum is always conserved, okay? What distinguishes them is the conservation of kinetic energy. In an elastic collision, the kinetic energy is conserved. In an inelastic collision, or a perfectly inelastic collision, the kinetic energy is not conserved as it is converted to heat between the two objects. And then lastly, do the masses interlock? And elastic and inelastic collisions, they do not, but in a perfectly inelastic collision, they do. Our two objects will interlock. So, determining types of collisions. So, to determine whether a certain collision is elastic or inelastic, what we do is we first apply conservation of momentum to determine any unknown quantities. In most cases, it tends to be a final velocity. Next, we determine the kinetic energy of each object before and after collision using the equation for kinetic energy or the kinetic energy momentum relation. K equals 1/2 mv squared or K equals p squared divided by 2m. Both equations are perfectly valid to use, but in some cases it's easier to work with this equation, 1/2 mv squared, and in some cases it's easier to work with p squared divided by 2m, as we'll see in class. Due to the squared term in each equation, you must use this relation for each individual object as opposed to the entire system at once. So you cannot add together the velocities of both your objects before collision and then square them. You have to take the kinetic energy of each object separately, each individual object as opposed to the entire system at once. Lastly, we compare the initial total kinetic energy to the final total kinetic energy in order to see if kinetic energy is conserved at collision. So let's look at an example. A billiard ball A, which has a mass of 2 kilograms, is moving to the left at 2 meters per second when it collides with a billiard ball B, mass of 1 kilogram, which is moving to the right at 3 meters per second. Determine if this is an elastic collision, provided that after the collision, ball B moves to the left at 1 meter per second. So again, we start out by applying conservation momentum. So we have the initial momentum of A plus the initial momentum of B. I use I here to indicate initial. And then we have the final momentum of A plus the final momentum of B. So we're going to have 2 kilograms times negative 2 meters per second, again because A is moving to the left at 2 meters per second, plus 1 kilogram times 3 meters per second, equals 2 kilograms times VAF, plus 1 kilogram times negative 1 meter per second, as ball B after the collision is moving to the left at 1 meter per second. So what that gives us as a result is negative 4 plus 3, I'm going to neglect units here a bit, equals 2 times VAF minus 1, which when we end up solving this equation is going to give us that the specific final velocity of our ball is going to be 0, as we get 0 equals 2 times VAF. So now what we do is we compute the initial and the final kinetic energies of our objects. So we have KAI plus KBI. In this case, I'm going to use PAI. I'm going to use the P squared divided by 2M relation. But in this case, you could also use the 1/2 MV squared relation. So either equation is perfectly fine used in this case. So we have PA squared over 2MA plus PB squared over 2MB. So we're going to have negative 4 squared divided by 2 times 2 kilograms plus 3 squared divided by 2 times 1 kilogram, which leaves us with initial kinetic energy when we crunch it out in our calculator of 8.5 joules. Now our final kinetic energy is KF plus KBF, but because the final speed of our object A is 0 meters per second, that tells us the final kinetic energy of A is also 0. So our final kinetic energy is going to be equal to the final kinetic energy of ball B, which is going to be, in this case, PBF squared divided by 2MB. PBF is going to be negative 1, so we square negative 1, divided by 2, which gives us a final kinetic energy of 0.5 joules. So as a result, we can see that the kinetic energy has been lost in collision. Specifically, we can see that the kinetic energy has decreased by 8 joules in this specific scenario. And this is the basic problem-solving process for determining whether a collision is elastic or inelastic.